Phone. All right. Wait, is that working? Hello. Okay. So at the end of the last lecture, we were talking about variable length arrays. And we've got this little example here where we have a function that inside the function there's a variable length array called ARR. And then we return that array at the end of the function. So this is an example of something you must never do. Right? That array there, it's a local array. So its lifetime is the lifetime of this function. Right? So as soon as this function returns, right? In other words, as soon as this line of code runs, that array is no longer guaranteed to exist. So if someone tries to use the array, like here, in the somewhere else, right? If they try to use the returned array, it's probably not going to work. Right, because the array no longer exists. So you must never return a pointer to a locally declared array. Right? But obviously there's lots of times when you're going to want to write a function where you have to return an array from the function. Right? So there's a few different ways to do it. But no matter how you do it, what you have to do is you can't create a local array. You have to do something else. And so that's what dynamically allocated memory is for. Right? So if you want to implement a data structure, like a stack, or a queue, or a list, or a set, or a map, right, then normally these data structures are implemented in a way such that they can grow. Right? So you have a list, you add something to the list, and it automatically grows in size to accommodate the new elements in the list. Right? Similarly, you might implement a list so that when you remove things, the size of the list shrinks as you remove things, although that's a little bit uncommon. All right, now, if you decide to implement such a data structure, right, what you cannot do is you cannot use arrays that have automatic storage. Right? In other words, you can't make little local arrays in all your functions and return those arrays, right? Because they disappear. Those arrays disappear as soon as the function returns. Right? So what do you do instead? Well, you might think, well, we've got this static modifier that we can use, and I know that anything that's static, its lifetime is the lifetime of the program. Right? But that doesn't work either, because every time you make a new list, you now need to make a new static variable, and there's no way to do that. Right? All your static variables are created at the time that your program first starts to run. So if you make a new list, or you make a new stack, or you make a new array, those things can't have static storage allocation. Right? So that doesn't work either. But we need a solution to this problem, and the solution is dynamically allocated memory. So dynamically allocated memory has a different type of storage duration. Its storage duration is called allocated storage duration. Right? So allocated storage duration simply means the lifetime of the allocated object begins when some function that allocates the memory for that thing returns, and it ends when you call another function that deallocates the memory for that thing. Right? So in C, the programmer has to manually manage the memory that the dynamic memory that they require. Right? Now, remember in Java and Python, right? So in Java, you type new blah. So what happens is the Java virtual machine takes care of allocating the memory for you for whatever blah is. Right? So you make a new object. The Java language takes care of allocating the memory for that object. In other words, the programmer doesn't have to do it manually. When the object is done, right? So when you're done with or when you no longer need the object, right? In other words, in Java, when you no longer have a reference to the object, then the language also takes care of getting rid of the memory for that object. Right? So languages like Python and Java, all this memory management is hidden from the programmer. But in C, you have to do everything yourself. So if you allocate memory for something, you're then responsible for deallocating the memory for that thing. Right? If you don't deallocate the memory for the thing, then you end up with what's called a memory leak. Right? So imagine you have some loop and you need to allocate memory for something over and over and over again. If you forget to deallocate the memory that you're allocating each time in the loop, right, that memory is never released back to the system, and eventually you'll run out of memory. So all of the memory management responsibilities now fall onto the programmer. Okay, so any memory that is dynamically allocated, that's actually the mechanics of allocating the actual memory and telling the C runtime where that memory is and so on and so forth. That's managed by an operating system thing called the memory manager. So that's actually not part of the C language. Right? So it's actually part of your operating system. So the memory manager implementations depend on the operating system and on your system architecture. Right? Some programs will even write their own memory manager to deal with memory. Because the operating system memory manager makes certain assumptions that might not apply to a particular program. Obviously, we're not going to do that in this course. Right? So the memory manager is responsible for the actual physical allocation of memory and managing any deallocated memory. All right, so a common way to do this is to use something called a heap. Right? So when you read any reference on C, you'll often see references to the stack and the heap. Right? The heap is where anything that's dynamically allocated comes from. Right? So the way this works is when the programmer asks for dynamically allocated memory, the memory allocator allocates a block of unused memory, marks that block as being used, and then returns a pointer to that memory block. Right? The requester is then responsible for, so as soon as the memory allocator finishes running, so it hands back a pointer to that memory, then it's hands off. Right? So now the programmer is responsible for managing that memory. So the programmer then is responsible to deallocate or free the memory when it's no longer needed. Right? So you have to give it back to the memory manager so that the memory manager can hand it back out to somebody else. Right? When you take your if you take your operating systems course, CISC220, you'll learn all about how these things work. So when do you have to dynamically allocate memory? Well, dynamically allocated memory is used when you don't know how much memory you need at compile time. Right? So in other words, if you have a program that reads in user input of some sort and stores that in an array of some kind, right, then you don't know how much input you may not know how much input the user is going to input. Right? So you probably need some sort of dynamically allocated memory here. Right? Similarly, if you have a list that's in a program, right, and the list, you want the list to grow and shrink as elements are added to the list or removed from the list, right, and you don't know how many elements will end up in the list, you need to use dynamically allocated memory. Now, one of the disadvantages of dynamically allocated memory is that it's less efficient, which means it's slower. Right? So it's slower than statically allocated memory. Right? And that's because there's this memory manager that has to run and allocate memory and give it back to you and so on and so forth. Right? The other problem with allocated memory is that if the programmer forgets to release back or deallocate the memory that they've used, you end up with a memory leak. Right? The memory manager never gets back the memory that it handed out, so it can't give that memory to some other process that's running. Okay, so how does this work? It turns out there's 3 functions that you need to know about. There's actually 4. So the 3 functions that allocate memory are called malloc, calloc, and realloc. These are defined in standard lib.h. I guess they're declared in standard lib.h. So those are the functions that will return back dynamically allocated memory. There's only one function for freeing or releasing any memory that has been that you no longer need, and that's called free. Right? So these are all defined in standard lib.h. Malloc is the one we're going to use most often in this course, but you can always use calloc or realloc. Right? So what malloc does is it attempts to allocate an uninitialized block of memory of a specified size. Okay, so there's a bunch of words here that you have to pay attention to. Right? Number one is it attempts to do so. Right? There's no guarantee that malloc will successfully. There's no guarantee that malloc succeeds. Right? So in other words, it's possible to run out of memory. Right? The memory manager may not be able to hand you back a block of memory that you request. Two, it's uninitialized. Right? So that means there could be anything in that block of memory. Right? In other words, you can't be guaranteed that the values in that memory are 0. Right? There could be anything in there. And three, you get back a block of the size that you ask for. Right? So if malloc succeeds, then you get back a block of memory that can accommodate the amount of memory that you need. Right? And the units of memory are in terms of the size of char in C. Right? So if you malloc 1 unit of memory, you can store 1 char in that memory. Right? If you malloc 2 units of memory, you can store 2 chars. Right? So if you need to allocate an array of int values, right? So I need 10 ints, then you need to allocate 10 times the size of int blocks of memory. If malloc successfully allocates a block of memory for you, then you get back a pointer to that block of memory. If it's unsuccessful, then you get null. Right? So you get back the null pointer if the request could not be fulfilled. So whenever you use malloc, you have to check the return value to make sure that it's not null. Right? Otherwise, you're going to use a null pointer, and that's going to cause all sorts of problems. So here's an example using malloc. So it's the exact same example as before, except when I make the array, right, I actually make a dynamically allocated array here. Right? So how do you make the array? So first of all, malloc returns a pointer. It doesn't return an array. Right? So it returns a pointer to something. So malloc here, how much memory do I want? I want n, right? Because I want to make an array of size n here. Right? But I want to make an array of int. Right? So how much memory do I need? I need n times the size of int, right? Blocks of memory. Right? Because again, malloc works in terms of size of char, right? Those are the units of memory that malloc works with. Right? So I need n chunks of memory. Each chunk of memory has size of int, right? So each chunk of memory can hold an int. Here, I don't actually check to see if he returns null or not. So I'm just going to assume that it's correct. You really should check, right? If array equals null, some sort of error has happened. Right? Now that I've got that dynamically allocated memory, I can return that pointer back to the caller. Right? Now, one of the funny things in C is that you can't return an array. Right? So here, I can't write int square bracket square bracket. Right? You have to return a pointer instead. Right? So I can return the pointer that's returned by malloc directly. And then down here, right, I can print that array. Right? Now notice that the array is not initialized at all. Right? So malloc gives you back a chunk of memory that's uninitialized. So there could be anything in this memory. Right? When I print the array, right, I shouldn't be surprised if I see I should not be surprised if I see some funny values in the array. Right? So let's see what happens when we run that. Oops, sorry. This is array malloc. Okay. So when we run that program, right, so let's make an array of size, I don't know, 15. Right. Press enter. Okay, so there it looks like we get back all zeros. Right. Try to make something bigger. Oh, sorry, it has to be less than 20. Right? And it still looks like I get back all zeros. Right? but you're not guaranteed to get back all zeros, right? So you have to be careful about assuming what's in that array, right? When you get back the array, you really should initialize the values in the array to something sensible, right? Because you could have anything in that array, right? It just happens to be the case that in this little program you get back all zeros, right? But that's not guaranteed to be the case. Okay, notice here when I'm done with the array, right? I don't use the array for anything else in this program because my main method is just printing the array, right? When I'm done with the array, I free the array by passing in the pointer to the free function, right? And so that will deallocate whatever memory was associated with the array, right? Once you free that pointer, you can no longer use that pointer. You can no longer dereference that pointer, right? So if you try to access the elements of the array after calling free, the results are undefined, right? Anything can happen. It might work, it might not. Right? So there's your, that's an example of malloc.
Professor,
hey,
memory management.
Sure.
So in terms of the dynamic memory usage here,
Yeah.
this array, is that external to the program itself?
What do you mean? Is
So
it?
where the program is allocated memory when
Yeah.
it's executed,
Yep.
is the malloc then within that actual allocated memory for the program?
No, it's somewhere else.
It's somewhere else.
Yeah. There's another way that you can call malloc, which you might find easier to use, right? So you can write, instead of writing n times the size of int, you can write size of, and then an array of int of size n, right? So either way is fine. It doesn't matter how you want to write it. They both work, right? So they both do the same thing in this case. Okay. If you really want to initialize the memory in a block of, so if you have dynamically allocated memory and you want to initialize it to all, you have to be a little bit careful with this one. If you want to initialize it to all zeros, then you can use the calloc function, right? So calloc does the exact same thing as malloc, except it sets all the bits in that memory to 0. Right, now that's not the same thing as saying all the values in the array that you get back are 0. Right? It's simply saying that all the bits are 0. And that's not necessarily the same thing. You have to be a little bit careful about this. Again, the size is measured in terms of the size of char. Right? So if you ask calloc for 1 block of memory, you get back enough memory to store 1 char. Right? And it returns the same thing that malloc does, right? It returns a pointer to the allocated memory, or it returns null if it couldn't allocate enough memory for you. Right? So using calloc, how do you use it? Well, it's almost the exact same thing, except it has 2 parameters instead. Right? So for calloc, you ask for n, right? N chunks of memory, each chunk of memory that big. Right? So in this case, I want to make an array of n ints. So n comma size of int. Right? So it has a different, its parameter list is different than for malloc. Right? Otherwise, it behaves the same. If you make an array of int, then calloc effectively initializes all the elements to 0. Right? If you make an array of something else, I can't think of an example where it's not, where if the bits are all 0, the values are not automatically 0. I'll try to come up with an example in the next class. So if you run this program, it's going to work exactly the same as the previous program, right? Except now you're guaranteed that the array, calloc, right? Now you're guaranteed though that when you print the array, it's going to be all zeros, right? So if you make an array, of length 10, you get back an array of int. You get back enough memory to hold 10 ints, and they all happen to be 0. I guess you can do the same. Oh, yeah, so this one's a little bit, instead of asking for n chunks of memory, each of size int, right? You can ask for 1 chunk of memory, equal to the size of an array of n ints. Right? So similar to using malloc, right? You can pass in the size of the entire array, but remember then you only want one of those, right? You don't want n of these, because that'll give you n squared ints. Oh, sorry. Okay, so that's calloc. Now what about realloc? If anybody has any questions about allocating memory, just fire it away. Okay, so malloc and calloc, they allocate a block of memory and that's it, right? So that's all they do. They give you a block of memory, you can use the memory for whatever you want. When you're done, you free it, right? Now, if you allocate an array using malloc or calloc, right? And you put some things into the array, and then you decide after the fact that I would like to put more things into the array, but I no longer have any space, right? Then malloc and calloc don't really help you, right? So what you end up having to do is you then malloc a new, bigger chunk of memory, copy all the old values from the old array into the new array, right? And then release the old array, right? So there's a function called realloc that will reallocate a block of memory for you. Right? So it reallocates any chunk of dynamically allocated memory. Right? So you can malloc or calloc or realloc a chunk of memory, and then later you can realloc the same block of memory. Right? As long as you don't free the memory beforehand. Okay? So the way you use realloc is you pass in a pointer. Right? So that's the pointer to the memory that should be reallocated. Right? And then you pass in the size in bytes, right? Of how much memory you want. It returns a pointer. Right? Notice it returns a void pointer. Right? So a pointer to void. So it doesn't actually return back a pointer of the type that you want. Right? So if you want an array of int, it doesn't actually return an array of int. You just store the result in an array in an int pointer, right? Excuse me. And it returns if it can't reallocate a block of memory, it returns the null pointer, right? Now, it's going to reallocate the memory that's pointed to by this pointer here, right? So that's what it's going to do. So if you have an existing array, you pass in the array to the function, right? If it succeeds, it's going to expand the amount of memory in that array, right? If it fails, right, your original array is still there, right? So it doesn't nuke your original array, right? You can still use the original array if realloc fails. If reallocation succeeds, then the contents of the original array, then the contents of the original array that fit into the reallocated memory are preserved, right? So realloc doesn't necessarily make a larger array. You can decrease the amount of memory that a block points. You can decrease the size of a previously allocated block of memory. Right? Anything that fits in the block is still there. Right? If you expand the size, then everything that was there is still there. Right? But like malloc, right? If you allocate extra memory, that extra memory is not initialized. Right? So anything could be sitting in that extra memory. Okay, so here's an example of, here's malloc. So this is going to be we're going to make an array using malloc, right? So this is the same example as before. But inside my main function now, right, I'm going to call make array once here, right? So that's going to make my original array using malloc, right? And then I'm going to reallocate that chunk of memory using realloc, right? So my array is going to be stored in ARR. Right? Down here, right, I'm going to call realloc. So I'm going to pass in the array that I previously allocated. Right? I'm going to change its size to whatever this value is. Right? And then it's going to return a pointer. So I'm going to create a new pointer or a variable to store the result. Right? If that new pointer is not null, right, then I'm going to make the old array, right, the old pointer point equal to the new pointer. Right? So in other words, I'm going to take my old pointer and point it to the newly allocated block of memory. right? There's no guarantee that realloc takes the original block and expands it, right? It is allowed to get some other chunk of memory and then move all the other stuff into the new chunk of memory, right? So when you reallocate the block, you have to reassign the original array back to the newly allocated block. Yeah?
Why don't you have to use reallocate or realloc in conjunction with and following malloc and force or calloc?
Run that by me again?
So I was thinking you can only use reallocate
Yeah.
after you've done the memory allocation with malloc
Yeah.
or with
calloc.
calloc.
Yeah.
So how can this function, or is it assuming that you've already used malloc somewhere else?
In this one, we have used it, right? So here, right, we made our array using make array, right? Make array uses malloc.
So we're
Yeah, yeah,
okay.
yeah. Right, and so yeah, so you have to, you can only reallocate a previously allocated block of memory. Right. And then again, notice that we free the block of memory when we're done at the end of the program. Right. Now this is just the main function, right? So if you don't free it here, the program stops here anyway. So the memory will be released back to the operating system once the program ends. Right? So this free here is kind of unnecessary. Okay, so let's try that one. What's it? Array. Right, so I'm going to make an array of size 1. Right, so I've got a 0 in it. I'm now going to try to expand that array to size 19. Right, and that succeeds. Ah, there we go, perfect. This is a good example. Right, so when I expand that array to size 19, right, the original 0 is still there, right, but then all the other memory that's been newly allocated, right, so all of this stuff here, right, there's no guarantee of what sits in that memory, right, and you can see here in this example, there's something funny sitting in that element there, right, so there's some uninitialized memory, or there's some memory that's got some value already, right, and it's not necessarily 0. So after you reallocate, you have to be careful not to immediately access one of the newly reallocated positions, right, because it might, there could be anything sitting there. I don't know what happens if you run the program again, if you get the exact same result. So let's try it. 1, let's try 15 this time. And I guess you do. So there's something about this program, there's something about the way this program uses memory so that that value is always sitting in memory when realloc runs. Okay, so that's actually the end of the lecture slide, but that's not where we should end this lecture. So I'm going to pull up code instead. All right, so there's something funny about this make array function, right? So this make array function, it returns an array of size n, right? It returns an array of int that can hold n elements, right? So when you call this function, right down here, where? Make array, right? So when you call that function, you can ask for an array of size n, right? But the programmer has to remember that that array can hold n elements, right? There's no way for the programmer to get the size of that array, right? In other words, right? So right here, right? So imagine that I forget the number of n for some reason, right? I no longer know what n is. And I want to know how big is this array, right? So a lot of programmers will say, well, I just use size of, right? So in other words, they're going to say something like size t, num elements, right? Sorry. So you might be tempted to write the following. Right? Because that worked when we had a locally allocated array, right? If you locally allocate an array, if you make a local array of whatever size, and then you call size of on that array, you get back the number of bytes used by that array, right? So divide by the size of the element type, and that gives you the number of elements, which I guess I should do here. right? So really I should write that divided by size of int, right? Because size of returns the number of bytes, the number of bytes that the thing takes up, right? So that's the number of elements, or I think that's the number of elements in my array, right? But if you print that out, %d, so num elements equals %d. Sorry, it's really hard to type on this tiny little keyboard. Okay, there we go. Right. So if I run this program now, so this is array realloc. So first compile. Right, size t is, so size t is long, is long. So I need to use LD. I guess I should use LU. Hang on. But anyway, this is fine. This will work for our purposes. Recompile. Okay. And then run. So I'm going to allocate an array whose size is less than 20. So I want to make an array of size 10. Right? Now, the program prints out how many elements? It says there's 2 elements in my array. Right? It doesn't say that there's 10. It says there's 2. Right? If you run this, so if I now say like 5, away we go. Right? Okay. So what's going on? Right? So the problem is the type of ARR. Right? So the type of ARR is a pointer. Right? So it's a pointer to an int. Right? What's the size of any pointer in C? Well, it's usually 4. Well, on my computer, it's 4. Right? It's normally the size of long, or unsigned long. Right? So that turns out to be 4 bytes, or 4 bytes, 64 bits. That's right, 4 bytes. Sorry, it's been a long day. 8. Right? So it should be 8. Right? So when I take 8 and divide it by 4, I get 2. Right? So your pointer sizes are always 8 bytes long, usually. Int is 2 bytes, 32 bits. 4. It's been a really long day. That's 8, that's 4, all right? So that's 8 and 4, that's why you get 2, right? So in other words, size of doesn't work with a dynamically allocated array, right? So if you write a function that reads a file, for example, right, stores each line of the file in an array, right, and then returns the array, there's no way for you to know how big that array is, right? Because in that example there, you don't know how big the file is to start with. So you're not calling make array with some value n, right? You don't know how big the thing is. Right? You're getting back some array, and you don't know how big the array you're getting back is. So if you write a function that returns an array, right, you also need to somehow tell the user or the caller how big is the array that's returned, right? And so the way you do that is as follows. So I'm just going to use, I guess I should make another function here. Okay, so let's also return an int array. So I'm going to call this make array 2, right? This time I'm not going to have a parameter that says how big the array is, right? So here I'm going to return an array of some size, some randomly chosen size, right? So I'm just going to do this. I'm just going to copy this, put it here, right? And for n, I'm just going to pick some value, right? So let's do 100, for example. All right. So when I call make array 2, right, if I can't see the implementation of the function, right, I don't know that it's an array of size 100 coming back. I just know that there's a pointer coming back, right? So if I call make array 2 here, let me change that to 2. Control S, do that. Compile. Line 19 here, 100. That's fine, right? Yeah. Recompile. Come on, there we go. Okay, and then run the program. Right. So again, so it doesn't matter what number you type in here. Right. It still says there's only 2 elements in that array. Right. Even though we know now it has 100. Right. So you have to convey back to the caller how big this array is. Right. Now, how do you do that? So this is returning a pointer, right? You can only return one thing from a function in C, so I can't return a second value, right? If this was Python, I'd just return a tuple where the second value tells you how big it is, right? But I can't. So what you can do, though, is you can take in another parameter, right? So I guess I should make it size type. Size t num elems, right? And then here, do num elems equals 100. Like that. And so when the caller calls this function, right, they're going to make a variable. Let me use this one. Control X. Control V. Right, they're going to pass in their parameter num elems, or their variable num elems, and hopefully the number of elements will be stored in that variable, right? So let's see what happens there. Right, recompile, sorry, control C, there. Recompile, rerun the program, right? This doesn't matter. Okay, well that didn't work, right? I got 0. So the number of elements in my array is 0, but, right, remember why this doesn't work, right? So this doesn't work, I can set, this works fine, right? I can set that parameter value to 100. Right? Now remember how C works? It works the same as Java and Python actually. Everything's passed by value. Right? So back here, when I passed in num elems, right, I didn't pass in that variable num elems, I passed in the number 0. Right? So up here, right, that's just 0. So when you set num elems to 100, that sets the value of the parameter to 100. Right? If I want to change the user's variable that they pass in, this has to be a pointer, right? So star. And then here, I need to dereference the pointer and then set its value to 100, right? When you call the function, you need to pass in a pointer to your variable that you want to store the number of elements in, right? So now the caller creates a variable, right, for the function to fill in the value of, right? The only way the function can fill in the value is if you pass it a pointer to that value, right? You can't pass in the, you can't just pass the variable itself because C passes the value of the variable to the function, right? So pass in a pointer to the variable where you want to store the number of elements, right? In the function, right? Change the parameter to a pointer, right? And then dereference the pointer and set the number of elements here, right? And now when you when you recompile and run this program, right? Now it tells you there's 100 elements in the allocated array, right? And so that's one way of dynamically allocating an array in a function, and then telling the caller how much memory, how big was the array that was allocated, right? And the problem is the caller needs to know how big that array is because they have no way of finding out otherwise, right? Which is kind of a problem, right? Yes. Here? I mean, you could make up a random number. So you could call the rand function. Here. Yeah, so you need I mean, it doesn't make sense without an example. So a common example is when you have to read a file or something, right? So if you read a file and you don't know how many lines are in the file, then you have to, so reading the file then becomes a problem. Because as you read the file, you probably allocate an array of some size. Then as you read the file, you check to see if you still have room in the array, right? When you don't have room in the array, you reallocate it and you keep going, right? But eventually you know how many lines are in the file, right? So in that example here, that's going to be, that 100 there will be the number of lines in the file. But you're going to be doing some sort of computation to compute how big that final array is, right? There is another way to do this. So there's another way. So instead, I can return the size of the allocated array. So this is make array 3. Right? So I can return the size of the array, but this time, the parameter is going to be where the user wants me to store the array. Right? Now, where do you store an array? Well, you need a pointer to store an array. Right? So int array, maybe? Maybe. Let's see if this works. So I'm just going to copy this, plunk it in here, and then instead I'm going to return. So in this case I'm going to return 100 because that's the size of my newly allocated array. Right? So here someone's going to pass me in a pointer. Right? I'm going to allocate space for the array and store it in that pointer, I hope. Right? I'm going to fill in the array with the values 0 through 99, and then I'm going to return back to the caller the number of elements in the array. Right? So that's make array 3. So let's take that out for a spin. I guess what do we do here? I guess we comment out these lines. Okay, so I make my variable, where's ARR? Okay, so ARR is right here. So I've already made my variable ARR, so I can just do size t. Num elems equals make array 3, like that. Right. Let's see if this works. Oh wait, make array. Oh, I have to pass in the array. Okay, so I need to pass in the pointer where I want the function to store the array. Right. So I'm going to do that. All right. Recompile. And run. Notice there's no compiler warning, right? Okay, so let's make an array of size. Actually, this statement doesn't make any sense. I should get rid of that. Okay, number of elements is 100, so that's good. It returns back 100. But then I immediately get a segmentation fault. Right? So this one barfs, and it barfs as soon as you try to print that array. Right? This worked, right? To print out the number of elements. Right? But here it barfed. Right, when you print out the number of when you try to print the array, right? Now, why did it barf, right? So it barfed because your array here was set to null, right? So in other words, there is no space allocated for the array, right? And you might say, well, no, that's not true because I passed ARR up to the function, and that function allocated space for the array, right? But what does that function need to do? Well, no, it returns the number of elements in the array, right? But what it needs to do is it needs to change, right, the value of the pointer that was passed to it, right? So in this function here, right, I needed to change the variable that stored the number of elements that was passed to it, right? I couldn't do it unless I passed in a pointer to that variable. Right? It's the exact same problem here. Right? Malloc's going to make a new array, and then I need to store that pointer somewhere. Right? So in other words, I need to change the user's value of ARR. Right? I need to change the user's value of ARR. Right? Whenever you need to change the user's value of some variable, you need a pointer to that variable. Right? So I need a pointer to a pointer. Right? So ARR is a pointer, but I need to change the value of that pointer. So I need a pointer to that pointer. Right? Now when I call the function, down here, where is it? Boop, 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 boop. Right? So instead of passing in the pointer array, right, I need to pass in the address of that pointer. Right? Yep. What's going on here? Array line 20. Oh yeah, right. I do need to fix that. Sorry. And then up here, I need to dereference ARR. So star like that. Right. Okay. Sometimes the compiler does help you. There we go. Okay. So make an array. Oh, it's still segment faults. Well, that's sad. Why did segment fault? It returned. It actually printed out the right value, right? Oh, yeah. I know why it's. Sorry, hang on. Make array. So I pass in the address of the array. So that gives me a pointer. And then I print the. That should work. Why did it barf? What did I do? Make array int star star. That's right. Oh, haha. Star array here. There we go. Okay. So I guess the compiler doesn't always help you. Okay, there we go. Now it works. Okay. 10. Oh, damn it. All right. So I was afraid of doing this because I didn't actually practice this before I came to class. I was like, oh, I should do this. And I didn't do it. What am I doing wrong? What time is it? Maybe I'll just end class there. I'm just going to end class there. I'm going to fix this for you and show you how to do this correctly next day. Sorry about that. Yeah, that was a little embarrassing, but stuff happens. All right, so we'll end it there. Anybody have any questions about the assignment that's due later tonight?
Yeah.
Yes, fire away. Question 3 is confusing. Init compile. The compiling one? Sorry? You don't get it? All right. You agree? Everybody's stuck on number 3? Okay. All right, so in number 3, I'm going to do what I shouldn't do. I'm going to try to do it on the fly. I don't actually have the solution on this computer. Let's see if I can do it. Okay, so number 3. This is going to be hilarious. All right, so root bin bash. This is init compile, right? Is that what it's called? I forget. Sorry? Yeah, okay. All right, so this program takes in I guess the command line arguments are a list of fully qualified class names, right? So, and then it's supposed to loop over all the directories and copy stuff from the directories into the packages that are created, right? So you can do this in one of 2 ways. It's going to be a nested loop either way you do it, right? You're either going to loop over the command line arguments or you're going to loop over the directories, right? It doesn't matter which way you do it first. I'm going to loop over the command line arguments. Right, so for each Java file in $@ do. Right, so that's just for, this is not Java, sorry, for each command line argument. Right? Okay, so each one of those command line arguments is a fully qualified class name. Right, so what you need to do is you need to figure out what's the package part of that name. Right, so get the package name here. Right, so JFile is a fully qualified class name. E.g., it's going to be something like my package dot my class. Right, so the very first thing you should do is get the package name for JFile, right? So here you want e.g. my.package. Right? Now, how do you do that? Well, there was the last shell scripting lecture. There was an example where you can find the extension of a file name, or you can find the part before the extension of a file name. Right? So the package is just the stuff that's before the extension. Right? You just view whatever the stuff is after the last period as the extension, right? Quote unquote the extension. The stuff before it, that's the package name. Right? So there's just a simple string substitution here that you can do, a simple string manipulation that you can do that gives you the part in front of the last period. Right? I actually don't remember what it is. It's some bizarre, I'd have to look it up. Right? Then you get the class name here. Right? So in this case, it's my class. Right? And again, in the lecture slides, there's an example where you can get the extension of a file. Right? So you have something .text. How do I get the .text? Right? Well, you can get there's a simple string manipulation that you can do that. Right? Then there's one slightly tricky line, if statement here to test if there is no package name. All right, so what I recommend you do is you just write this loop, right, and see what you get. So print out the package name and print out the class name, right, and see what you get when there's no package name, right? So in other words, if someone calls the program init compile my class, right, see what you get for the package name and class name, right? As soon as you see that, you'll realize what the if statement is here to deal with the case where there's no package name, right? And that's it. So now you've got your class name, you've got your package name. Now all you do is loop over the directories, right? So for each student dir, each stu-dir in star, right? Because the assignment says that all the subdirectories are just student directories, right? So you don't have to do ls blah, 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 or anything like that, right? Just do for student dir in star. Okay, so I now want to, so what do I want to do? Okay, so if there's no package name, if no package, then you're done. Then done. Right? If there's no package, there's nothing to do, right? Because you can just compile the student's file directly in their directory. Right? But otherwise, right, else, right? So here, if there is a package, then you have to do something, right? So if there's a package, use, what's it called? Make package, right? Make package to make the package directories. Right? That's easy to do, right? You just write make package and then the name of the package, right? That's how you use that. That's how you use the script from assignment 2, right? So literally, it's make package and then $package, right? Where package name is the variable that stores the name of the package, of the current package, right? And then you actually want a command substitution here, because you need the output from make package to get the actual directory, right? So dir equals command substitution. Voila, right? So there's your directory. Now what do? You copy the Java file into that directory. Right? So copy, and you know the Java file because you've got the class name up here. Right? Copy the Java file into dir, and you're done. It's actually not that long. Right? It's supposed to be a short question. It's literally like less than 30 lines long, I think, if you code it all up. That's it. Right? You can do it either way, right? So you can either loop over the student dirs first and then internally loop over the package names, or you can do it this way. I think it's easier to do it this way. So that's it. Okay.